Hello guys, welcome to Fitted Technologies. In today's video, we're going to simulate a basic example of how to simulate plate with hole using Abaqus. This is good if you're a beginner in Abaqus. I will show you the basic steps like creating materials, assigning materials, creating partition, making mesh, good mesh, and making partition, making independent mesh, dependent mesh, what are the difference, create load displacement, and removing the mesh from your simulation result so you can see a very good counter plot and many other things. So stay tuned if you think this is helpful for you. Okay guys, so let's now work on it. Click here, create model database with a standard and explicit model. We click here, create part, and 3D deformable solid. We're going to try and solid. And then let's make here 0, 0, and then make 100 by 100, so it's a 10 by 10 centimeter plate. All right, and now we want to create a hole here. I'm not sure where's the here. Oh, let's create 50, 50, so it's right in the middle. And then just click anywhere in this vertical location. Then we will click here, add dimension, click here the circular, and click here. Let's put some number here. I think 5 mm radius is enough, so the hole is small enough, right? And then you click here and then you click done. And then the depth, I want to make it quite thin. In this case, thin, maybe around 2 mm. Yeah, usually it's a thin plate with 2 mm thickness. Yeah, so this is our part. So we can actually work like this. All right, so you can go to the mesh. If you want to do meshing, you can do meshing directly here. Yes, but it doesn't look good, or you can make it smaller. This is how you set the size of the mesh seat part. Yeah, you can put 2 mm. The default was 5, so Abaqus can calculate the default value. This is the recommended value by Abaqus, but it's usually quite big, so I make it smaller value around 2. Click apply, delete meshes, okay, and then we create here, click mesh part. You click and then yes, but still it doesn't look good. So what you want to do usually is to make partition. So we need to go back. You can do it here, but I prefer to go back to the part so you don't confuse. So for each part, in this case we only have one part, so you don't have to worry. We create here we directly partition cell. So in Abaqus, this is called a cell, right? As already explained in previous videos. This is called a cell because this is a, so they call it face, cells, and edge and vertex. Vertex is this point, edge is this line, face is one face like this, one face, and then this is the cell, right? So it's a solid entity. So we want to partition cell, define cutting plane. Here there will be a pop-up because we already mesh it. If you haven't meshed, there is no pop-up warning like this. So it says that if you want to partition, then your mesh will be gone. Is it okay? Yeah, it's okay, right? And then we use 3 points. There are so many options. Here I'm going to use 3 points. The idea of 3 points is that you need to specify 3 points that defines your cutting plane. Okay, so how will you cut the cell? So here I will divide them like this. I choose the center part, I choose here, I choose here. So you can imagine that there is a virtual plane there, or we call it a datum plane, that is going to cut this cell. So if you click here, create partition, or you can press the wheel on your mouse, you can just press down. Sometimes I press down. So if suddenly it continue to the next step without me having to move my mouse here, it means I already pressed down the wheel on my mouse. Okay, so here I click the create partition. Done. It's now partitioned into two cells, right? So now let's make another partition. Select the cells to partition. Now we have two cells, and then we want to divide these cells with this cutting plane, right? So click here, or you can drag them, and then you can press the wheel down, click like that, and then you choose 3 points, or you can just click continue. Okay, and then I want to click here, and then where is it here? I cannot see. You can rotate. The way you rotate is you press Control Alt in your keyboard, and then you drag the mouse. Okay, you click here and you click here. Okay, here, here. Okay, so 3 points, and then you create partition. You click here, or you can just press the wheel. Now it's partitioned nicely. Okay, so when you want to model this, for example, let me explain to you. Let's go to the mesh. Let's go to the seed, and now it's 2, right? Because we already set it before. And then you go to the mesh part like this. Usually, for example, if you apply the loading here, there will be stress concentration in this area, right? Because this area will be loaded significantly because of the shape of the crack, while this area, they have less stress concentration. The highest concentration is here, and here. Why? Because your loading is to the y direction. Okay, here, this direction. So the maximum stress is here. So what you want to do is to make a fine mesh around here. Okay, now we cannot. So here you can assign a local seed edges. So this edges is seeding locally. So you want to assign like more number of elements here. But here, if you try to choose here, it will select this line, the whole line. But actually, you don't need this area to have a lot of mesh. You just need this area, because you know that the stress concentration is a lot here. So it's better to create another partition. So we divide this line into two lines. Okay, so you go back to the part, create another partition here, and then let's click here. And you will just, instead of clicking done for the next, I hope you understand, I will just press my wheel down. Okay, and then okay, like 3 points. So my cutting plane is this, and then I rotate, Control Alt and drag, and then here and here. So this is my cutting plane. Okay, okay, now you can do for the rest. Okay, click okay, 3 points, click here, yeah, okay, you click here, you click here, then create partition and do it again. Done. 3 points, click here, click here, click here. Okay, now I also want to show you how to zoom in to zoom out detail. So the way to zoom in to zoom out is by scrolling the wheel on the mouse. Okay, like this. But this is a normal scroll. Sometimes if you zoom in like this, you want to zoom out quickly, you can press Control while scrolling. So it's faster usually, instead of doing it slowly like this. You can do it very fast if you press the control how you call it, keyboard, the control key on your keyboard, yeah, while scrolling the mouse. It's faster zoom in, faster zoom out. Okay, now sorry, now let's the other one. Let's make partition. Do this guy, 3 points. Select the first point. Okay, here, here, and here, and done. Okay, click done because it's finished. Now if you click here, this is the front view. Now it's nice. We will apply the loading in the y direction, and we will make a boundary condition here at this point. So first let's go to the mesh. Next, the meshing. We set the global sit part. Okay, now it's the local. So what you want to do is you click here, so you can specify the number. If you go the number, they will only use 2 elements, but you don't want it to. You want to make it, if you want to define by size, the size is now 1.9, right? So with this 1.9, there will be 2 elements around this and 2 here. But because you want to capture the stress concentration, you might want to increase, right? So you can increase it like 5, and the way you increase can be set. For example, if you do it like this, it means that the size of the element will be uniformly distributed, like they have the same size here. Okay, click OK, and then click done. Let's create the mesh first so you understand. So this is what I mean. So they all have the same, but sometimes you want to make a non-uniform mesh. For example, you can choose this bias. So the bias will make, let's do it one by one. This is what I mean. If you choose bias, as the location goes to here, the mesh will be more dense. For example, delete mesh. You see, now this is big, 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 small, smaller, 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 and it's getting small as you reach here. It's why we need like this, because we want to capture the highest stress concentration around this area. All right, so this is the most important area. So we can do it again for this one. Oops, sorry. Let's do it here. Click done. Single. Delete and then click OK. Oh, you see, this is big, smaller, smaller, smaller. We make a mistake in the direction. So we can click here again. Click done. So this is the direction. Note that the arrow is here, so it means that as you go here, it is going to be smaller. That's not what we want. What we want is that as we go here, we want to be smaller here. So we need to flip the arrow, the flip bias, flip, and then click apply. So now it's getting smaller there. And then you want to, let's say 9 element, like this one. So Dito, one more question. What is the difference between single and double? No, it's just how they distribute this variation. If you click double, yeah, they will have more elements here and more elements here. So basically you have two arrows, right? So the bigger will be in the middle. When you single, you have only one direction. From here to here, it's getting smaller here. When you have double, you will have minimum size of element here and small element here. In this case, we want to be single. Okay, and then you can click mesh. That's great. So now if you see, my element is better here than here. So in reality, when you create model for your research, you want to do the same thing here. But for the sake of simplicity, I will just leave it like this, okay? This is also quite strange. This is the Abaqus, settings. If we actually set the global seeds around 2, so basically there should be 2 here, but the effect of global local seed size, they affect this size too. And note here that we only set here, so it affects this element only, but not this. So if you see here, there is a little bit tilted because we only enforce the the local seed size with bias here, not in this age. So you need to do it with the same thing here. Okay, if you want, we flip, we put a 9 element. Okay, and then the same thing here. You put the 9 element here. Okay, done. And then you create side, you create mesh, click yes. Now it's everywhere at this face and also this face, but not here. Okay, so it's great. You can, for example, like this, you can also make these customized mesh sheet. The stress concentration usually maximum here. I mean, there's a lot of variation here, so you don't want to have like a uniform size of elements along this direction. You want to have bias also that set very fine mesh around here. So you can also click here. Yeah, click here, click done. There will be 23, and then you can flip. So there is more elements here, and then you can increase 30, apply, delete the mesh, and click OK, and then click done, and then click here, mesh part, and yes. As you can see here, as it goes here, you have more elements. This is big, bigger, smaller, big, 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 smaller, 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 and it's getting smaller as you go here. All right, so if you want to capture the stress concentration here, this is better than just simply leave it like this. Okay, too much talk about meshing. Now let's continue to the properties. This is a standard mechanical elastic properties. So you click here, mechanical elastic. Let's choose a 70,000. So this is 70,000 MPa or 70 GPa or around 0.3. So this is a typical value for aluminum, I think. And then you click OK. You create section here, and then you create assign section. So there are 3 steps here. First, create the material, create the section, and assign the section. 1, 2, 3. We did the first one now here. This is a very simple process. Just choose, because this is cell solid. So you choose solid, and then they're homogeneous. They're not composite. So choose homogeneous. If you want to do composite, you can click here, composite. Now we use here, continue, click OK. And then now we assign this section that we just created. You want to check what set or what section available. Click here, section manager. There are 1 section only, the one that we just created. And if you want to check the materials that you have created so far, you click here, material manager, only material 1. You can also rename if you want, dismiss, and then click here, assign. We assign to this guy. Okay, then click done. And then you can see here, it's called section 1. The type is solid, homogeneous, and the material is material 1. And you click OK. This is how you check. Okay, so before you click OK, make sure you check the material is correct and the solid is correct. In our case, we only have 1 material, so there will be no error, I think, in doing this. Okay, and I click OK, and then click here, You don't need again. As you see here, as you assign the sections, the color change from the gray gray cells to now it's become green cells. Okay, now go to the assembly. You click here. So basically, the part is just part. It's basically things that you have in your workshop, right, or in your model, in your file. But when you do simulation, what you simulate is what's in assembly lines. Okay, this is what you're simulating. So you can have many parts, but maybe in some cases you have so many parts, like 1,000 parts, but you don't want to simulate these 1,000 parts all together. You want to make assemble of several parts. So you just need to choose things that you want to simulate. You need to assemble things that you want to simulate only. So this is how you create, and this is called instance. So instance is basically the part that you choose to simulate. So you create the instance of that part. Some part maybe already exists in your model, but you don't create the instance because you don't want to simulate it. Maybe for some reason you have it there. So we create instance, and you choose what part that you want to simulate. So you need to create instance of that part. So here we only have one part, that's why it's only there. If you have 100, you can choose which one you want, right? And then you click OK. So actually, the instance type, there are two types. There is what we call independent type, there is dependent type. So in this case, we already choose it, we already mesh it before, right? So before we create the assembly, we already mesh, we already create the element. So if you do that, it's basically they will do it, they will set the instance, this instance, as a dependent part. Okay, so you might have a question, what is the difference between independent and dependent, Dito? It's quite simple actually. Independent means that you are doing this meshing. Yeah, so when you do meshing, you do the meshing for the instance, while you, if you choose dependent, you do the meshing on the part. So imagine that one part I create, for example, if I click here, I can create like multiple instance of one part. If I mesh on dependent, the meshing here and the meshing here will be exactly the same because I'm meshing the part. So the mesh, the element size will always follow the part. So this instance will follow the meshing on the part. This instance will also follow the meshing on the part. So they will always have the same mesh. When you choose independent, you have the freedom to make this mesh on this instance different from the mesh on this instance. So that is the only difference. Okay, independent or dependent. So when do we need that, Dito? Imagine that you have bowl, like you have one part of the bowl, and then you use this bowl for example, 20 locations, and depending on the load, the contact location might be different. So you want to make the mesh will be different, maybe for, you know, for different purpose, because at one location the contact area maybe on the left side of the bowl, so you want to make the mesh on the left side of the bowl more refined, while on the other bowl the contact part is on the right side, so you want to make the mesh finer on the right side. So in that case, if you choose mesh on dependent or mesh on part, you cannot do different meshing style on this bowl. They will always have the same style of meshing, and that's what you don't want, because the contact area different depending on the location of the the bowl on the system, or it depends on the loading, right? I hope you understand what I mean, right? So the idea is how the mesh will be on this instance. If you use dependent on part, all instance will have the same meshing style, meshing settings, and all that. While if you use independent, you can, how you call it, just justify, not just, you can adjust different meshing style for different instance. Okay, too much talk. I think you understand. Okay, cancel. So I only have, so basically you click here, you choose, and then you click OK. But I already make one step, and then click here. But one thing before I move, be careful when you create the mesh. You don't want to click apply and then click OK. If you click apply and click OK, you will create two instances from one part, because once you click apply, it's actually creating one instance. Click apply again, one instance. So if you click apply, you create one instance. You click OK, you create one instance. Sometimes the instance will be in the same location. So you click apply, you click OK. They're in some one location. So here, actually, there are two. In this case, it's one. But imagine if I click again, actually here, there are two instances, but they are in the same locations. So when you create simulations, sometimes you didn't assign material property or boundary condition. There will be error at the end, and that will confuse you. So be careful. If you want to make sure that you don't create two instances in the same location, always choose auto offset. So the second instance will not be in the same location. They will put slightly translated to the right side. So you know that, oh, if I click apply, and then if I click OK, they will be here. They will not overlap. So you know you make mistake. So in this case, as you see, we have created three instances, but we actually at this location we created two instances. Let's check how to check that. It's from here. Where is it? Assembly. Yeah, instance 4. There is one here. There is instance 2 here, the same location. 3, 4 is here. So we don't need this. Let's delete this. And also this, we don't need. We just need one. It's really important. Beginner usually tends to click apply and OK, and then they didn't realize that at that location there are two instances. So when they give loading or a boundary condition, they only give loading and boundary condition to one instance, because they forgot that at that location there should be a two instance. Actually, when they're running simulation, they will see that, oh, there's error because you are forgot to give boundary conditions. Yeah, because actually there are two instances if you click apply and OK. So be careful in this assembly. Okay, and then let's go to the step. So this is step. So basically this is telling how the simulation is going to take. Like, is it going to be 1 second compression, 2-second compression? So create steps, or how the simulation is going to take place. For example, in sheet metal forming, you might want to compress the edges of the plate, and then the indenter will press from the middle, making the forming process. So in that case, you need two steps. First, the step for compressing the edges of the plate. The second is the indentation process. So this is why you need to create steps. So you need to set or to tell Abaqus how the process is going to take, what kind of loading will happen. So here we just need one step. The default is that you need to create one step in addition to the initial step. So initial step is the default step in Abaqus. You don't need to do anything in the initial step. You need to create another step, right? The step that is going to load your samples. In this case, it's just simply pulling the plate away. So you just need to have another step. Continue, click on. You don't have non-linear geometry, so because it's usually very small loading, so you can just use off. In non-linear geometry, if you have a lot of deflection, like high deformation, like in bending, or imagine you want to simulate a bridge that is deforming 1 meter, 2 meters, like the rotation is more than 10 degree, 15 degree. In that case, you need to turn on the non-linear geometry. Otherwise, you don't need. And then this is the minimum time step. This is the initial time step. This is the number of increments. So I will not explain here in detail because the video will be too long. I will make another video about focusing, understanding the step model. Okay, click here. So you can click here. There's initial, there's step 1, static, general, off, nonlinear geometry, because we will just give a small loading, and then we will have fill output manager opened, and then we edit here. So we need to, so the idea here is that Abaqus will give you the output for each one increment. If you do it every one increment, they will give you output. In our case, we don't need too much output for us. We just need to have like fill output or like a contour plot only at a given interval. Like for example, in our case here, we choose evenly spaced time intervals. So let's choose 20. So basically, if the simulation takes 1 second, every 1 to 20th second, they will give us one contour plot. So we will have in total 20 frames of simulations. What kind of contour plot that you want to have is stress, strain, displacement, force, contact, and so on. And click OK here. We also set here fill output, history output. Double click here. We also want to evenly space it. Then the interval is 20. And then here usually we only need the energy if you need, otherwise you don't need to check this history output. You can just leave it as default. And then interaction, here there is no interaction because we only have one plate. So if you have multiple plate, you might want to set the contact. In our case, because this is the beginner level tutorials, we'll not do any contact. And then giving the loading. The loading is pretty simple. In this direction, we are going to fix, while in this direction, we are going to pull in the Y direction. So click here. So you can do it many ways. You can do displacement control here. So you fix, while here you can give the force directly, like in newtons, or you can put the, how you call it, the displacement. Like for example, you pull this area 1 millimeters away. Yeah. If you want to do the load, you can create load like here. There's so many load. You can put pressure. So there is pressure up. It depends to you, or H load, surface traction, many kinds of load. In this case, I will not use this one. I will use this create boundary conditions, displacement rotations, and then you can put the name. I will say pulling load. So continue. Make sure you move it so that you choose not the edges but this surface. You can zoom in again, click here, and then press shift if you want to select multiple face. Okay, shift and click, and then click done. And then you want to pull in Y direction. How much? Just for example 1 millimeter. So the size is 100. 1 millimeter is like 1%. Click OK. And then you want to rotate. Create here, create boundary conditions. The same thing here. Okay, click done here. And then to 0. So what we are doing here is basically we're pulling here and then preventing this guy to move in Y directions. But also we need to make sure that they will not move in the Y direction and the Z directions. So let's create boundary condition here at this line to make sure you have the symmetry. We create here, create boundary condition, displacement. Just choose this line. You can also choose 1 point. It's just to prevent the translation or rigid body motion. In this case, I choose this line, and I choose this. What is this? Y. And then for the Z directions, You can also click displacement rotation, continue. I click here, or I can click here. So basically this will not move in the Z direction. The Z direction is this plane direction, okay? So basically I will just choose this point, or you can choose this line if you want. The result will be the same. This here. So you might have a question, what is UR1? The UR is basically the rotation. In 3D elements, in 3D cases, these are by default 0 because there's no rotation degree of freedom for nodes in the solid elements. Remember this. In basic, I said basic because maybe people can have fancy element formulation for cell or for solid element where they will have this rotation. But for basic general element that we are using in daily life, for solid applications, for solid elements, usually the nodes do not have rotation degree of freedom. It's just translation in 3 direction, ux, uy, and uz. There is no rotation, okay? So even if you click here, or if you don't click there, these 3 things, they're all the same. They're all the same for solid element, But if you use, for example, shell elements or beam elements, you need to set this guy, okay? Okay, and then now let's do the job. We'll give the load, we give the mesh right here, and then let's go to the job and then create job, and you can put any name you want. I leave it job 1. Continue. I have 4. This is parallelizations. If your computer has 4 cores, you can put 4. If you have 8 cores, you can put 8. You can put any number you want. It doesn't have to be a, how to say, it doesn't have to be an even number. You can put odd number like 3, 5. It's okay. In my case, my computer has 4. I don't want to use all of them. I can just use 2. This is the precisions in Abaqus standard, or the standard general as we choose in the step. Abaqus, when calculating, by default always use double precisions. Double precision means that when they're calculating, the number of floating point behind the comma, behind this decimal point, is around 16. If you use single precision, I think it's only 8. So if you want to get accurate simulation, always use double precision. In Abaqus standard, they always use double precision. In Abaqus explicit, you need to set it manually. Otherwise, the default is to use 8 floating point, or how you call it, or single precision. So you need to manually set double precision if you use Abaqus explicit. For the current simulation that we're using, it's using static general, it's using Abaqus standard. They always use double precision. And the nodal output, the way the output will be written, it can be single or full. Double precision, you always use full. This is not really important because even if they give you data output, like they said the maximum stress here is 24 comma blah 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 blah, blah megapascal, maybe what you need is just like 2 comma, right? But when they're doing calculation, they need to do it accurately, right? But for you, for data interpretation, this is not really relevant. Even if they give you like output 16 digit accuracy, in your report you will not put 16 digit, right? You just, like, important digit is just like 2 digit or 3 digit for you, or even 1 digit. So yeah, okay, let's put full. Okay, and click here job manager and click submit. And let's wait. It's running, so it's good if it's running. So let's check the status of our simulations monitor. So this is the job 1 monitor. The status is running. So this is the increment. Oh, this is the step time. Now it reaches 1. It's quick. It's very fast because it's very simple model, linear elastic model with only few elements. It's completed now. because if you remember, we set the period of the simulation is 1. So if you remember, go to step, you click here, step manager, time is 1. So it says it incremented here, it's here, the maximum, no, not here, here. The time period is 1. So how long this pooling process happens? It happens around 1 seconds, right? It happens in 1 second. So what Abaqus did, if you check here in the monitor, they try to do it very small, 0.05, and it works. Yeah, so they only iterate 1 time and it works. They try to do it 0.05, and as you can see here, they finish in 20 increments. And this is the way you see the output. As I said before, there is 20 output frames because we set them to give us output at evenly spaced time interval. How many intervals? We set 20, that's why now we have 20. Okay. The warnings, you don't really need to be like care a lot, right? As long as it's not like really important things. Error, as long as there's no error, it's good. Dismiss. Now we check the results and click here. Okay. You can see here there's a bit strange here. So it's pulling very nice, but there's a problem here. There's like out of plane movement, right? As you can see here. What, you know why? Because we didn't fix this, how you call it, the Z plane. So if you want to make it correct, previously we just, for the BC4, we just choose 1 point. This is not enough. That's why if we want to give like uniaxial loading, we cannot just push this, because due to numerical error there is out of plane movement. So you can click here if you want. You can choose the new set. Let's make set 5, and then choose, click here, click first to remove this line, this point, because previously this point was selected. Now click here, nothing is selected. Now select this, press shift, this, okay, and click done. Okay, so now it's good job, and submit again, click OK again. It will be pretty fast, I think. Okay, all right, so it's 20% already. It should be pretty fast. 0.70%. Now it's done. Dismiss, and now click result. Status completed. Click results. So they are very good right now. Okay, as you can see here, they're pretty good. There's like this butterfly pattern. This is the stress concentration. Right, very nice. So how many times the stress concentrate or amplify in the tip? Usually it's around 3 times for infinitely width wide element. If the plate is so wide and the circular is so small compared to the size of the plate, the stress here is 3 times the normal stress here. So if you check here, the stress here is around 7, or I don't know, 6. All right, now here is 1.5 maximum, so it's around 3 times. And there's a bed deformation here, I think. Yeah, it's because there is a a lot of stress concentration here. Okay, or if you want, we can put a better mesh, or if you want to see how to probe the element or the value here, dito. So this is the stress. The phone is a stress. If you want to probe the value here, sometimes it's gone because my laptop is too small. You need to move it a little bit below. This is the probe values. So this element has 1522, while this element is 678. So 1522, it's around 2.5 times. Okay, so it's good, right? So it's usually around 3, I think. So if you make it smaller, it will be around 3, depending about there's like the effect of finite size of the plate, right? So this is a good simulation. So this is how you should do it. This is good for your practice. First simulation, you can study the effect of this bias. You can improve the bias if you want, and check what is the effect. And I will show you in another video how to do this very same simulations with a better. For example, we will not model the whole thing, but we will only model the quarter of it. You can click here also. This is very important. Sometimes you want to remove the elements, right? Yeah. So this is nice to be put in the report paper, as you can see here. And there's like something like this. This is called H effect because we have two white. Okay. I think it's great, right? There's a bit warning here that I'm a bit worried. It says that distorted element usually. I think these elements here are a bit distorted. You don't want that to happen. And let's go to the mesh. Let's go map part. So you cannot modify from here because our mesh is not on assembly but on part. So let's make 1 or 1.5. And then you can click here verify mesh to make sure that all the mesh are good. So as you can see here, this area will give you warning. No, I think this one is better. This one is important. Okay. Yeah, so these elements are not meshed very well because of these edges. Yeah. Maybe we want to increase it more. I don't know, maybe 40. Okay, now let's check. Highlights, still they're not good. Yeah, but that's okay. That's okay. Let's run again. Or check if it's getting better. Okay, so it's already reaching 1 hour videos. It's just about the basic tutorial of how to do mesh, things that you need to know as a basic Abaqus users. But this is something that you need to learn, like understanding what is different between independent or dependent part or instance, and why you have to choose bias, when not to choose bias, and so on. This is good for you to understand. Yeah. There is like this effect here because I don't know why. If we remove this For example, I think it's better to remove this guy. If you want to delete this, yeah, done. I know, because we create this, but we didn't do it for this guy, and that's create a strange thing. You want to do it, you need to do it for both of them. Okay, now let's do it. Let's make it for 40. Make sure also the the leg. Okay, select again. Yeah, so basically I flip them, then I click OK. Now both of them has been set. Okay, now let's do the simulations. I think if we click submit, it will be very fast, don't worry. It's gonna take like 10 seconds and it's done. I think there shouldn't be any. Still 700 element distorted. I think it's okay. Yeah, I think it's okay. As long as we don't have these strange deformations around these edges. Okay. You see? Yeah, now we don't have it, right? We don't have it then, and it's really nice. And as you can see here, more stress concentration here, because now we can capture pretty well, because more elements are very fine here. If we want to show it again, click here, common options, and exterior, apply. Yeah, so more elements here, that so you can capture more stress gradient around this area compared to this one. And as you can see here, there's no strange deformation here. The previously strange deformation is due to the fact that we assign this bias here, but we don't assign the bias at this one, so they don't have the same setting, right? So it's really nice right now. Dito, I pull it up and 1 millimeters, right, Dito? Yes. I want to check the reaction force. How can I get? How can I check the reaction force? You can click here, create XY data. The data is on the ODB field output. Continue. And then we want to check the reaction data on the places that we put the constraint. So it's on the nodal, unique nodal. Okay. And the reaction force, this is in the Y direction, so RF2. So the elements now, you can choose one by click edit and then choose which node that you want to check, edit. Okay, and then select nodes for the one that you want to create the reaction force. But in this case, we don't want to select one by one. It's already there, because when we create a nodal a load, when we create a displacement fix here, we already create the set for that. So the node set, click highlight so you know which set. Not set 1, yeah, set 2, set 3 is only there, set 4 is only there, so it's set 2, right? And then save. Let me show you first. It's 0. When you click save, it will generate all the data for all the nodes here. Okay, so many nodes here, as you can see. Now you don't want the data for each node, you want to have the summation of all the forces. So you can create here, operate on XY data, continue, and then you click here, sum, there, and then you click the first data, and then until the last data, and then before you click, press shift first, and then click, and then add to expression, then save data, sum, the summation. So this is the new data, basically the summation of all this data above. and then you can plot it, and then you can check. Okay, this is the force reach how much is this? I don't know. You can scroll to zoom in. So it's 0.136 to the power of 6 Newton. So because we was Newton millimeter and MPa, so in the unit we use MPa millimeter, so the force should be in Newton. So it's like mega Newton or 136 kilonewton. Okay, so that's how you plot. So how can I get this data to Excel dito? And you click XY data manager. In this you can double click and then you click here, and then you can copy, right click, copy and paste to your Excel spreadsheet. Okay, and then you can plot your report and so on. So enough for today. I hope you understand, and bye bye. Don't forget to click like and subscribe to this channel. Okay,